Okay, let's just jump right in. We're about to explore a field of science that, honestly, sounds like it's straight out of a sci-fi novel, but it is absolutely real. Welcome to the hidden world of information geometry. So, I want you to just picture this for a second. What if we could draw a map, not of a place, but of knowledge itself? A map of ideas, of data. I mean, what would that even look like? Well, believe it or not, we actually can. And that is the whole idea behind information geometry. It lets us see information not as some boring, flat spreadsheet, but as a rich, three-dimensional landscape with its own geography. Its own hills, valleys, and even hidden shortcuts. All right, so let's unroll this new kind of map and take a look at the hidden geography of data. Okay, so the real key here is that last little bit, spaces of probability distributions. It sounds complicated, but that's just the fancy term for the actual terrain we're mapping. See, every single point on this map isn't a city or a town. It's a statistical model, a unique way of looking at a chunk of data. And this whole field uses the powerful tools of geometry to find the hidden connections between all of them. Now, to explore this grand new world, your standard compass and ruler just aren't going to cut it. Nope, we need a totally specialized geometric toolkit, one that's custom built for this unique information landscape. Think about it, right? Every map needs a scale, a way to measure distance. How far is it from this idea to that one? Well, to figure that out, we're going to need a pretty special ruler. And here it is, the Fisher information metric. Now, it's called a Riemannian metric, which is really just a fancy way of saying it's a ruler that works on curved surfaces, not just flat ones, and it's invariant, which is super important. It means you get the same measurement no matter which way you turn the map. It's basically the universal standard of measurement in this world. Okay, so we've got a ruler to measure a path along a curve. That's great. But what about the distance between two totally separate points on our map? How do we actually put a number on how different two ideas, two statistical models really are? For that, we have something called divergence. It measures the separation on what's called a manifold. That's just the math term for our information landscape. You should think of it less like a simple distance and more like, well, like how different two things are. It tells you how much information gets lost when you try to describe one point using another. And here's the wild part. It's not symmetrical. The distance from idea A to idea B often isn't the same as from B back to A. It's a really cool concept pioneered by brilliant minds like Shunichi Amari. And just like a real explorer has a whole bag of tools, there are different kinds of divergence measures. You've got the famous KL divergence, the Bhattacharya distance, the Matsushita distance. You pick the right tool for the specific terrain you're charting. All right, I hope you're ready because this is where things get really, really interesting. This whole landscape, it's a bit mind-bending. We're about to step into a world of duality. I want you to imagine you have two maps of the exact same place. Maybe one is a road map and the other shows you all the mountains and valleys. Neither map is wrong, right? They're just different views. And you kind of need both to really understand the area. Well, information geometry has something just like that baked right into its DNA. Technically, these views are called dual connections. But let's not get bogged down in the jargon. Here's what matters. When you use both of these maps together, you get the complete picture. And this dual perspective is so powerful, it actually lets us use a new, generalized version of the Pythagorean theorem, but for this curved world of information. It's this incredible link between ancient geometry and cutting-edge data science. Okay, so this is all really cool theory, but you're probably wondering, so what? What's the actual payoff? Where do these maps lead in the real world? Well, let's take a look. I mean, the list of applications is just staggering. We're talking machine learning, AI, quantum information, statistical physics, neural networks, economics, computer vision, signal processing. The list goes on and on. This is not some tiny niche academic thing. This is a foundational toolkit for so much of modern science. Let me give you a concrete example. Think about machine learning. An algorithm might be looking at a huge cluster of data points. Now, instead of just finding the simple, boring average, information geometry helps it find the true center of gravity of that information. It's a way smarter, way more natural method for finding the single point that best represents the entire cluster. And honestly, it gets even bigger than that. We're not just talking about mapping data on a hard drive. We're using these exact same principles to map the deep, fundamental geometric structures of the universe itself. Now, look at this quote. I know it sounds super complex, but the core idea is actually beautiful. What it's saying is that down at the quantum level, the most efficient way to do something, the shortest possible path for calculation, isn't a straight line. It's a curve, a geodesic through this landscape of quantum information. This geometry is literally woven into the fabric of reality. And all of this brings us right to the edge of our map, to the unexplored territories, and what the future holds for this incredible information landscape. So if there's one thing you take away from all this, let it be this. Information isn't flat. It's not just a lifeless table of numbers in a spreadsheet. It has shape. It has curves, hills, and valleys. A hidden geometry that fundamentally affects how ideas connect to one another. And that, ultimately, is the gift of information geometry. It's so much more than just abstract math. It's a new language. It's the map and the compass that we need to finally explore and navigate the hidden shape of knowledge itself. Which leaves us with one last really big question to chew on. If information has a geometry, what other massive hidden structures are out there just waiting to be mapped? What else is hiding right in front of us, just waiting for us to find the right tools to see it?